Hello everyone, and welcome to this video on orthogonal vectors. So in this video I'm going to start off by defining what it means for two vectors in an inner product space to be considered orthogonal. And I'll also define what it means for two vectors to be orthonormal. Then we'll go over several examples where I'm given two vectors from a specific inner product space, and asked to determine if they are orthogonal, orthonormal, or neither. Alright, so what does it mean for two vectors in an inner product space to be orthogonal? So two vectors, say u and v, from an inner product space V are orthogonal if the inner product of those two vectors, right, the inner product of u with v, is equal to the number 0. Right. Now, if these two vectors, u and v, are also unit vectors, right, meaning that their norms are both equal to 1, right, so the norm of u is 1, the norm of v is also 1, and their inner product is 0, right, so if you have two orthogonal vectors that are also unit vectors, then they would call u and v orthonormal vectors. If you recall, the process of normalizing a vector was to find a unit vector in the same direction. So here the concept of normal or normality means having a norm of 1. All right, and this ortho prefix will correspond to having an inner product of 0. Now, a little note to make here. Very often you'll hear the words orthogonal and perpendicular tossed around. When the inner product is the dot product, right, so the standard Euclidean inner product, when the inner product on a vector space is the dot product, right, and specifically on Euclidean spaces R2 and R3, right, things that you can actually picture, two-dimensional and three-dimensional Euclidean space. When the inner product is the dot product on R2 and R3, the word orthogonal will basically mean the same thing as our typical notion of the word perpendicular. All right, remember, perpendicular vectors, or two lines are perpendicular if they meet or intersect at a 90-degree angle. I remember that was usually denoted by like a little box like this, so these two lines I just drew would be considered perpendicular. When the inner product is the dot product on R2 or R3, vectors that are orthogonal will also be perpendicular in the under the typical notion of what it means to be, perpendicular, right? That they form a 90-degree angle at their intersection, right? Or if you were to draw them with the same initial point, they'd form a 90-degree angle. Now, that's only when the inner product is the dot product. All right. If the inner product is some other function, not the dot product, the word orthogonal will not necessarily mean perpendicular in the typical sense that we're used to seeing the word perpendicular, right? What it means to cross at 90-degree angles. So you'll see with other inner products, right, on other inner product spaces where the dot product, is not the inner product, I'll be strictly using the words orthogonal instead of perpendicular. All right. So as I just kind of mentioned, right, the dot product isn't we've seen this before. The dot product isn't the only inner product on Euclidean space. So, two vectors may be orthogonal under one inner product, say the dot product or something, but, not orthogonal under a different inner product. All right, so, their inner product under one inner product may be 0, but under a different inner product may not be 0. Okay. So again, that's why I'm not going to throw around the word perpendicular too often, right? We'll stick to orthogonal for the most part. All right, so let's look at an example where the inner product, where we're looking at a couple vectors in R2. All right. So here's a picture of a couple vectors in R2. I've got a nice little grid work here. My vectors are u is the vector with components 6 and 4. V with components -6 and 9, and I've drawn them here on the standard coordinate plane, like the xy plane. Vector u, and I've drawn them both as position vectors where the initial point is at the origin. Vector u tells me go right 6 up 4 for that motion, right 6 up 4. So here's vector u, right, going from the origin to the point 6, 4. And vector v tells me go left 6 up 9. So from the origin here, left 6 up 9. So there's vector v, this arrow, from the origin to the point -6, 9. Now, when you look at these two vectors, and maybe if I turn it this way, maybe it's clear that these vectors are perpendicular, right? They form a 90-degree angle. I'll make a little box notation here, a little perpendicular notation, right? So these vectors are perpendicular under the common notion of the word perpendicular, right? They form a 90-degree angle, a pi/2 radian angle, however you want to think about that. They're perpendicular. But be careful, just because vectors are perpendicular in the usual sense of perpendicular doesn't mean that they're always orthogonal. All right, like I said at the top here, whether or not two vectors are orthogonal depends on how the inner product is defined on that vector space. All right, so just because you see, hey, vectors are perpendicular, that doesn't mean they're orthogonal. All right, they may be orthogonal in under one inner product, but not orthogonal under a different inner product. So let me show you what I mean by that. All right, so taking these same two vectors, 6, 4 and -6, 9. Let's say I want to find the inner product of these two vectors when the inner product is the dot product. All right. So remember, I said earlier, when it's the dot product on R2, R3, right, spaces you can actually picture. When vectors are perpendicular, the dot product will be 0. All right, we'll see that happen here, right? We saw in my picture these two vectors, 6, 4, and -6, 9, they do look like they're forming a 90-degree angle. So their dot product should be 0, and let's see that. All right. So the inner product of u and v, under this rule, right, where the inner product is the dot product, is, remember, the product of you take the product of the first two components, right, 6 times -6, and add to that the product of the second components, 4 times 9. That's -36 plus 36. That is indeed 0. Right? And if the inner product of two vectors is 0, then those vectors are considered orthogonal. So we would say that U and V are orthogonal under this inner product, right, under the dot product. All right, but be careful, right? Like I said, the whether or not two vectors are orthogonal strictly depends on how the inner product is defined. So let's take the same two vectors, okay, U and V, same components, but now this time, part 2 here, I'm going to find the inner product of these two vectors when this is the definition of the inner product, right? Not the dot product. But the inner product of U and V is twice the product of their first components plus 3 times the product of their second components. All right, and this is one of those weighted Euclidean products, right, where it looks like the dot product is similar, but the coefficients are, other positive numbers besides 1 all the time. All right, so let's find this. Right? What is this inner product? So the inner product of U with V, this time, right, using this rule, is 2 times the product of their first components, 6 and -6, plus 3 times the product of their second components, 4 and 9. So this is 2 times -36, right? So -72 plus, and then 3 times 36, 108. But, this is basically -2 36s plus 3 36s. That's 136. This is 36. Positive 36. Which, notice, is not 0. So when the inner product is defined this way on R2, these two vectors are not considered orthogonal. So again, really be careful, really pay attention to how the inner product is defined. And usually if the inner product is not defined, you can assume the dot product. Assume the standard inner product. Alright, so since, again, down here for this second inner product, the inner product of these two vectors, the 6, 4 and -6, 9, was not 0. So U and V are not orthogonal under this inner product. Okay, but not orthogonal. So I'll say it one more time. You just got to really pay attention, right? What inner product is being used on that vector space, right? Okay. Now, some other symbolism here. So back in the part 1, when we say two vectors are orthogonal, you can use this symbolism, U and like an upside down T, almost like a, this is like the symbol for perpendicular. You could also write that, U is orthogonal with V. U and V are orthogonal vectors under this inner product, under the dot product here. And if you just put a little slash through that, when I say that they are not orthogonal, that means U is, not orthogonal to vector V, right? Just a little slash. It's like a slash through any symbol means not that, right? And this would be totally acceptable to me anyway. Not orthogonal. Now again, I caution, right? Again, I caution using this all the time because people very often confuse this because you're used to seeing it in geometry with perpendicular. Just because, again, like I said, just because two vectors are perpendicular doesn't mean they're orthogonal underneath under certain inner products. You know, there might be perpendicular vectors that are orthogonal under other inner products besides the dot product, right? I don't have an example of that. I'm sorry. All right, so just be aware. Right? The symbol's fine, but you know, just because two vectors are orthogonal under a certain inner product doesn't necessarily mean they're perpendicular, you know, by the standard definition of perpendicular. Okay, because like, you know, this inner product down here, you know, there are vectors where this inner product would be 0 that are not, when you look at them, forming a 90-degree angle. Okay, so now I want to talk about a question you should ask yourself, right? Or a question that may be asked of you. Well, now that I know, you know, under the dot product, right, going back to the dot product, now that I know under the dot product these two vectors are orthogonal, the question maybe now is, you know, are u and v orthonormal? Orthonormal. If you know, so we have to find the norms. Right? We have to find the norms of these vectors using, you know, the inner product, the dot product. Right, so let's check. So are u and v orthonormal under the dot product? So let's find the norm of u. Remember, the norm of a vector was defined to be in an inner product space was defined to be the square root of the inner product of that vector with itself. All right. Well, remember here, this is the dot product, right? I'm using the dot product here. You know, when the vectors are orthogonal. So my inner product is the dot product. So we have the square root of the dot product of u with u. So, you know, 6 squared plus 4 squared, which is the square root of 50, right? 36 plus 16, the square root of 52. Sorry, 36 plus 16. The square root of 52, which, you know, we can break this up to 2 times the square root of 13, right? The square root of 4 times the square root of 13. Now notice that this is not 1. Right? The norm of vector u under the dot product, the norm is not 1, telling me that, you know, u is not a unit vector. And that means that u and v, they're orthogonal, but they're not orthonormal. Right? So u and v are orthogonal. Right? U is orthogonal to v, but they are not orthonormal. In this, because their length, their magnitudes, their norms are not both 1. All right, well, what if I asked you now to take these vectors, right, these orthogonal vectors, and find two vectors in the same directions that are orthonormal? So what if I asked to do that? So since they're not orthonormal, what if I said instead, let's find two vectors in the directions of u and v that are orthonormal. Well, that's simply a matter of normalizing these vectors. I brought this up in a previous video. To normalize a vector is to simply find a unit vector that's running in the same direction, right? That's just a positive scalar multiple of the original vector. So this is normalize the vectors. Now it's very easy to find a unit vector when you're given a vector and you want to find a unit vector that goes in the same direction. You simply multiply by the reciprocal of its norm. So like you see that the vector 6, 4, its norm is 2 times the square root of 13. If I want to write a vector that's in the same direction as u, but with a length of 1 or a norm of 1, I just multiply by the reciprocal. So I take 1 over the norm of u times u. This will be a unit vector. So this is 1 over 2 times the square root of 13 times the vector 6, 4, and here's this vector. When I multiply these two, I get 3 over the square root of 13, and if you want to rationalize that, make it 3 root 13 over 13, go ahead. And then multiplying these two, 2 goes into 4 twice, that's 2 over the square root of 13. And there you go, right? Maybe I'll call this u prime or something, right? Vector u prime. There, it's a vector that's in the same direction as u, but the norm of u prime, right? The norm of this new vector with the components 3 over the square root of 13 and 2 over the square root of 13, the norm of that vector is 1. And then I'm going to do the same thing for vector v. Alright, so I'll pull up another page and let's do the same thing for vector v. Alright, so what's the norm of v? Again, it's just the square, the norm of a vector under any inner product space is defined as the square root of the inner product of that vector with itself, and here the inner product is the dot product. So this is square root of negative 6 squared plus 9 squared. So 36 plus 81, 117. Right, the square root of 117, which 9 goes into this evenly, right? 9 goes into this 13 times. So this is equal to 3 times the square root of 13. Again, that's not 1, right? So my vector v is not a unit vector, but I can easily find a unit vector that goes in the same direction, right, by simply multiplying v, this negative 6, 9 vector, by the reciprocal of its norm. So 1 over the norm of v multiplied by v, right, this is going to give me a unit vector in the same direction. So this is 1 divided by 3 root 13. Right, that was the norm of v, times vector v was this vector with components negative 6 and 9. And multiplying the top ones, you have negative 6 over 3 is negative 2. So negative 2 divided by the square root of 13. And then multiplying by the 9, that's 3 divided by the square root of 13. And again, I'll call this v prime. Right. There's another one. The norm of v prime the norm of this new vector will be 1 unit. So there we have, that's how you change orthogonal vectors into orthonormal vectors. You simply normalize each vector, multiply each vector by the reciprocal of its norm. Right. So the set of vectors, right, vectors u prime and v prime. Right, u prime was this vector here, right, with the components positive 3 over the square root of 13, and then positive 2 over the square root of 13, and vector v prime that I had there, which has components, negative 2 divided by the square root of 13, and then positive 3 divided by the square root of 13. These vectors are orthonormal. Their inner product, which in this case is again the dot product, their inner product is 0, and they're both unit vectors, are orthonormal. And one more time, what does that mean? Right, orthonormal means their inner product is equal to 0, and each vector has a norm of 1. Right? Each one of the vectors is a unit vector. That's what it means to be orthonormal. So, one way to put this that might help you, reason some stuff out. So, if a pair of vectors, every pair of orthonormal vectors is orthogonal, but not every pair of orthogonal vectors is orthonormal. Right? So as we saw, these two vectors under the dot product are orthogonal, but not orthonormal. Right? They're orthogonal, but not orthonormal. These two vectors, however, under the dot product, they're orthonormal, so that means they must be orthogonal, right? Orthonormal vectors are orthogonal vectors with, lengths of 1, norms of 1. But orthogonal vectors, where the norms aren't both all 1, are not orthonormal. I don't know how else to put that, right? Just pay attention to the norms as well as whether or not their inner product is 0. All right. So that was an example involving a couple vectors from R2, and I had one inner product, the dot product, that the vectors were orthogonal under. And if you have a set of orthogonal vectors, you just normalize those vectors, and then you'll have a set of orthonormal vectors. And then under a different inner product, right? Remember that 2 times u1 v1 plus 3 times u2 v2. The same two vectors were not orthogonal. Right, so really, really pay attention to what the definition of the inner product is. And that's what I have for the last couple examples in this video. All right, so we're looking at different inner product spaces this time, right? So not just R2 or R3 or something like that. So I'm asking myself to determine whether the given vectors are orthogonal, orthonormal, or neither, under the specified inner product. Right, so pay attention to the inner product. So my vectors here are some functions that are continuous over the interval from -3 to 3. So p of x is the 1 plus x, q of x equals x minus x squared. These are polynomial functions, so they're continuous everywhere. But so they're definitely continuous on the closed interval from -3 to 3 on the real number line. So these belong to that vector space, right? The set of all continuous functions on the interval from -3 to 3. Where the inner product on this space is that integral inner product, right? I'll do the integral from -3 to 3 of f times g. If I'm doing the inner product of two functions, it's the integral over that interval from -3 to 3, right, of the product of those two functions with respect to x. So if I want to determine if these vectors are orthogonal under this inner product, I just take their inner product and see if it's 0 or not. All right. So are P and Q orthogonal? So what is the inner product of P and Q, right, these two functions here? So this would be the integral from -3 to 3 of P times Q, right, 1 plus x times x minus x squared, and then, with respect to x. Alright, so this will be a nice little polynomial. It's the integral from -3 to 3 of, I'd have negative x cubed, and then plus x squared minus x squared, so no x squareds, and then minus x squared. Oh, sorry, not minus x squared, plus x. Alright, so you have x, minus x squared, plus x squared, so no x squareds, and then minus x cubed. So negative x cubed plus x with respect to x. And, you could do the antiderivative here, but you might recall that, this is an odd polynomial, right? All the powers are odd. Right? X to the third, x to the first. And this is an odd function. And if you recall, you integrate an odd function from -a to a, right? Here's -3 to 3. That will be 0. Right? Go ahead and take -1/4 x to the fourth plus a half x squared. Plugging in 3 and -3 will give you the same value, and then you'd be subtracting them and get 0. Right? So the inner product of these two vectors, right, these two functions under this inner product is 0. So this tells me that P and Q, right, these two functions are orthogonal. Right, and it's assumed under this inner product. I'm not going to keep writing under this inner product. Right, should just know that. Right, that's assumed. Now the question becomes, hey, okay, so their inner product is 0. Are the vectors orthonormal? Right, so their inner product is 0, that's half of it. Are the norms of these vectors both 1? Right. Right, so since they're orthogonal, again, the next thing, the question after that is, are P and Q orthonormal? So let's find the norm of P, the norm of P of x. Remember, the norm is defined as the square root of the inner product of that vector with itself. I'll just write P and P. Alright, so what is this? Now, we have the inner product of P with itself is the integral from -3 to 3 of P times P, right? Remember the inner product was the integral from -3 to 3 of the product of those polynomials, those functions. Right? So 1 plus x times 1 plus x. So 1 plus x squared. Then with respect to x. Okay. Now again, this wouldn't be too terrible to find by hand, right? Just multiplying a polynomial out. But I do have a nice little calculator here to make this a little quicker. So on the TI-84 plus, right, hit the math button, hit number, you can just hit number 9, have an integral come up, and then I'm going -3 to, oops, I hit enter too soon. All right, so -3 to 3 of the quantity 1 plus x squared, and all of that with respect to x. So this is 24, right? Nothing too terrible. So the norm of p is definitely not 1, right? So the norm of p is equal to, the square root of 24 under this inner product, which you can simplify as, square root of 4 times square root of 6. That's 2 times the square root of 6, which is, like I said, not 1. So I don't need to check q. Right? I don't need to check q. Since one of these is not a unit vector, right? That means that p of x equals, 1 plus x is not a unit vector under this inner product. And if any one of the vectors is not a unit vector under that inner product, then, they're just straight up orthogonal and not orthonormal. Right, so P and Q are not orthonormal. But like earlier, what if I said, okay, I know that they're orthogonal, right? I know that these two polynomials here are orthogonal under this inner product. What if I wanted other functions that were orthonormal and in the same direction as P and Q? All right. Well, just like before, I'm going to normalize these vectors. So I have the norm of P, right? So I've already told you that they're not orthonormal. Okay, got that much. But what if I want to now find a pair of orthonormal vectors, using P and Q? So let's normalize. Let's normalize P of x equals 1 plus x, and Q of x equals, what was it, x minus x squared. Alright, so we already saw that the norm of P was 2 times the square root of 6. We already saw that, right? That was right here. So this vector, 1 divided by the norm of P times P of x, right? The reciprocal of the norm of P times P will be a unit vector. And it's going to be a unit vector in the direction of P, meaning just a positive scalar multiple of P. Will be a unit vector. Alright, so this is 1 divided by 2 root 6 times 1 plus x. Alright, and if you'd like to distribute, that's 1 over 2 root 6 plus 1 over 2 root 6 times x. And let me call this f, right? I haven't used f and g yet. That was p and q. I don't want to call it p prime because you might confuse that with derivative. Alright, this is not the derivative of p. So here's a polynomial that would be a unit vector under this inner product. Alright, this integral inner product. Alright, and let's do the same thing for q. Right, q of x was x minus x squared. Let's find the norm of q. Remember, that's the square root of the inner product of Q with itself. So this is the square root of the integral from -3 to 3 of, Q squared, the product of Q and Q. So the quantity x minus x squared, and then with respect to x. And again, I'm just going to go in and type this in as it is with the square root and everything to get the norm of Q. All right. So we have the square root of the integral from -3 to 3 of the quantity x minus x squared, that quantity squared dx. And that's all underneath the square root. Alright, and then let me square that just to see what the integral was. It was 115.2. Alright. So again, this is let's say this is the square root of 115 and a fifth. So that'd be 577 fifths. Right. The square root of 577 fifths. Alright, 115 times 5 be 575 plus 2 fifths. Yeah, 577 fifths. So then this vector. So then 1 divided by the norm of Q, that scalar, right, the reciprocal of the norm of Q, times Q of x, this will be a unit vector. And let's see what that would give me. That's 1, well, instead of the square root of 577 fifths, it'd be the square root of 5 over 577. Alright, that'd be the reciprocal. Times Q of x times x minus x squared. And, well, let's leave it at that. You can distribute the square root if you want, but there you go. This is a unit vector, a vector with a norm of 1 under this inner product, this integral inner product. And I'll call this g of x, instead of q prime, because I don't want to confuse with derivative. And then there you have it. These two vectors, this function f here and this function g here would be orthonormal. This 1 over 2 root 6 plus 1 over 2 root 6 times x, and this square root of 5/577 times the quantity x squared, x minus x squared. Right. So if you were to integrate the product of these two, you'd get 0 from -3 to 3. And if you take their norms, right, they both have a norm of 1. So their inner product is 0, and they both have a norm of 1. That's what it means to be orthonormal. Alright, so I'm not going to do this normalizing with the last example. I just simply want to check, are the vectors orthogonal, orthonormal, or neither under the specified inner product. Alright, so this time my vectors are 2 by 2 matrices. So A is this matrix with rows 2, -5, 1, 0. B is this matrix with rows -3, -2, -3, and 7. These belong to the vector space, R 2 by 2, right? The set of 2 by 2 matrices with real entries. Or you might see this as M 2 by 2, just 2 by 2 matrices. And the inner product defined on R 2 by 2 here is that the inner product of two matrices is the trace of the transpose of the first times the second. So if you take the transpose of the first matrix, multiply it by the second matrix, and find the trace. Now remember, the trace of a square matrix was the sum of the main diagonal entries. But you've probably seen in previous videos of mine that this particular this operation here is the Frobenius, what's called the Frobenius inner product, where I simply take matrix A and B the way they are, and it's almost like the dot product. I would multiply multiply the corresponding entries and add them up. All right. So let's see. Are these two vectors, our matrices A and B here, orthogonal under this inner product? So let's find the inner product of these two matrices. Yeah. Getting pretty faint there. We'll toss it. All right, so what's the inner product of the matrix I was given A and the matrix B? Like I said, you can find what A transpose times B is and then just add up the main diagonal entries. You can do that if you want, or it'll give you the same result as for performing this Frobenius inner product on matrices, which is just multiply the corresponding entries of A and B and add them up. So 2 times negative 3, those are the first row, first column entries of A and B, plus, and then negative 5 times negative 2, right, the second row, first row, second column entries, plus, and then 1 times negative 3, the second row, first column entries, plus, and then 0 times 7, the second row, second column entries. All right, so that's negative 6 plus 10 minus 3 plus 0. So this is 1. All right, this is 1, which is not 0. Okay, so this inner product applied to these two matrices does not give me a result of 0. So under this inner product, right, this Frobenius inner product, matrix A and matrix B, right, these two vectors are not orthogonal. And that's all we could say, really. Right? Because if they're not orthogonal, I can't just normalize the vectors and make them orthonormal all of a sudden. All right. Yeah, so that's all I can really say. Their inner product isn't 0. So under this particular inner product, these vectors, these matrices in this case, are not orthogonal. All right, and that's that. All right, so again, just pay attention to what inner product space you're in, right? How is the inner product defined? And that will determine, whether or not you have orthogonal vectors or not, right? You take the inner product of the two vectors. If the inner product is equal to 0, they're considered orthogonal. If it's not equal to 0, they're not orthogonal. And if they are orthogonal, a reasonable follow-up question would be, are they orthonormal? So then you take a look at their norms, the norms of the vectors, right? And if they're orthogonal and all the norms are 1, right, they're all unit vectors, then they've considered the vectors orthonormal. Now, if they're orthogonal and not orthonormal, you can very easily make them orthonormal by normalizing each vector, multiplying each vector by the reciprocal of its norm. And you'll get a set of orthonormal vectors that are in the same direction, right, that are just positive scalar multiples of the original orthogonal vectors. All right, so hopefully that was clear. When to determine orthogonality of vectors, or orthonormality of vectors, right? Some fancy words. And hope you enjoy practicing problems like this, and thank you very much for watching.